Hello, this is Mason Haggerty with question 8.49 from the textbook Fundamentals of Heat and Mass Transfer, 8th edition. So in this question, we have a hot fluid passing through a thin-walled tube of 10 millimeter diameter and 1 meter length with a coolant at 25 degrees Celsius in cross flow over the tube. When the flow rate is 18 kilograms per hour and the inlet temperature is 85 degrees Celsius, the outlet temperature is 78 degrees Celsius. So there's the diagram here. Again, we have the hot fluid with the coolant. There's the tube, and it's all in crossflow. So we're assuming that the fully developed flow and thermal conditions in the tube, we want to determine the outlet temperature, TMO, if the flow rate is increased by a factor of 2, so doubled. That is, the flow rate is 36 kilogram per hour, with all other conditions the same. The thermophysical properties of the hot fluid are density equals 1,079 kilogram per cubic meter. The CP equals 2637 joules per kilogram Kelvin. Mu is equal to 0.034 Newton second per meter squared. And K equals 0.261 watts per meter Kelvin. So we're assuming steady state, constant properties, fully developed flow, neglect effect on heat transfer except convection. So we're not assuming that. We're going to assume there's no radiation or anything. So I've summarized case 1 here. We have T infinity equals 25 degrees Celsius, which is equal to 298 Kelvin. The mass flow rate is 18 kilogram per hour. TMI is equal to 358, and again, that is the inside of the tube. And then TMO is equal to 351, and that is the outlet. So that's the inlet and outlet temperatures. In case 2, we know that T infinity equals 298, same thing, but mass flow is now 36 kilograms per hour. But we are also still assuming that the T in, so the TM in, is equal to 358 Kelvin, and we are trying to find the TMO. So I continued again just to tabulate the properties and dimensions. These are all just given in the question before, although I did find the volume, which is equal to just pi times 0.005 meters squared times 1 meter, which gives us our volume of 7.854 times 10 to the negative 5th meters cubed. And the surface area is 0.01 meters times 1 meter times pi, which equals just pi over 100 meters squared. So for analysis, so to begin, we are looking at the delta T outside outlet over delta T inlet. So you have T infinity minus T outlet of inside over T infinity minus TM inlet, which equals E to the power of negative UA surface area over M dot CP, which is equation 8.45a in the book. So for case 1, we know all of the necessary values to find the U, which is the heat transfer coefficient. So you have 298 minus 351 over 298 minus 358, all Kelvin, equals E to the negative U times the surface area, which is pi over 100 meters squared, over M dot, which is 18 kilograms per hour, but we're going to convert it to per second, so you divide it by 60 squared. Multiplied by CP, which was given as 2,637 joules per kilogram Kelvin. So you want to rearrange this, and you're trying to find U. So you're going to get that, simplify out all that and kind of rewrite it. You're getting that 0.8833 is equal to the E to the power of negative 2.383 times 10 to the negative 4th times U. So solving for that, you find that U is equal to negative 2.383 times 10 to the negative 4th times ln of 0.8833, which equals 52.06 watt per meter squared Kelvin. So that is that part. Then we're going to find the Reynolds number, and we're pulling the one for the circular tube with incompressible flow, which is equation 8.6 in your book. And so this gets us 4 times m naught over pi d mu, which is the viscosity. So that's going to get you 4 times 18 over 60 squared. Again, that's the mass flow in kilogram per second. Over pi times the diameter, which is 0.01 meters, times mu, which is 0.0034. You solve that out, you get that it's 187.24, which is well below 2,300, which is the cutoff for laminar. So you know that this is laminar fully developed flow. And then we are looking at the case 2, and we just use the same equation, but you double the mass flow, and that is still laminar. So H does not change because the laminar it's still both laminar and fully developed. So for C2, you have everything stays the same except now go back to the equation where it's delta T O versus delta T N, and you just refill in the values, but this time you have U, but you do not have TMO, and you once again just rearrange this equation, and you're going to get that 298 Kelvin minus e to the power of negative 52.06 times pi over 100 meters squared over 36 over 60 squared kilogram per second times 2,637 joules per kilogram Kelvin multiplied by 298 minus 358 Kelvin is equal to TMO, which is equal to 354.39 Kelvin. So your outlet temperature, when converted to Celsius, is 81.39 Celsius.